There we go. So I'm Lauren. I'm talking about some of the work I've been doing on floor fracture craters. So it's a talk sort of in two parts. The first part will analyze my work using the LROC imagery and LOLA data to classify floor fracture craters and to map their distribution across the lunar surface. And then the second part of the talk will talk about how we're using these data to examine the two formation hypotheses for floor fracture craters, which are viscous relaxation and magmatic intrusion, and then to further examine the actual mechanics of magmatic intrusion. So to start off, floor fracture craters are anomalously shallow craters with fractured floors, and they were characterized beautifully in a work by Schultz in 1976 and also further work. Some of the other characteristics of floor fracture craters include moats, ridges, mare patches, and dark halos. And all of these characteristics serve to define the different morphologic subclasses of floor fracture craters. Right here we have some lovely LOLA topography that shows just how different these craters are from normal craters. There. So to give a sort of catalog of the different morphologies observed in floor fracture craters, see right here the crater Gassendi, characterized by a wide moat, most prominent on the basinward side of the crater. And then there's also the crater Gaudibert, which looks very different. It's characterized by this high inner ridge, which in some places even higher in elevation than the crater rim crest. It also has this domed central floor region, which is very unusual. And there's the crater Vitello, which has strong concentric fractures around the uplifted central region. And then the crater Humboldt, which has these prominent radial fractures and the patches of mare material along the edges of the crater. So I carried out an extensive search of the lunar surface to categorize all of the floor fracture craters I could find, and then mapped the distribution across the lunar surface by subclass. And it's rather jumbled on this chart, but there are prominent trends that can be observed in the distribution of these subclasses. So two of the most striking observations about the relationship between the classes and their location are that craters close to basin edges typically have flatter floors, stronger uplift features, and many more fractures, such as the crater Gassendi seen earlier. Whereas craters farther in the highland material have more convex up domed floors, less overall total uplift, and less prominent fractures. And so these two trends could be indicative of the formation mechanism of the craters. It could be due to thermal effects close to the impact basins, which would be more tied to a formation by viscous relaxation, or they could be the effects of intrusion close to maria and sources of magma, as would be in the case of a magmatic intrusion formation. So then use the morphologies we observed to test these two proposed formation mechanisms, as both viscous relaxation and magmatic intrusion have distinct effects on the observed morphology of the crater. In the cartoon on the left, you can see some of the effects of these two formation mechanisms on the crater morphology. So in the case of viscous relaxation, there is a long wavelength amplitude decrease in all of the crater topography. So the rim crest height decreases, the floor appears to shallow, and the relative height of the central peak to the floor decreases. Whereas in the case of a formation by magmatic intrusion, the rim crest height is left unaltered, the relative height of the central peak is unaltered, but the floor appears to be much shallower than in the regular complex crater case. There are using the observed morphologies of the floor fracture craters, we hypothesize that magmatic intrusion is the much more probable formation mechanism. And this is because there is a significant decrease in floor depth. In many of these craters, it is a kilometer or greater decrease in floor depth, and this would require unreasonably high thermal gradients to viscously relax the crater floor to that amount. There's also an unchanged rim crest height in these craters. If you were to plot the rim crest height of a normal crater population and the floor fracture crater population, there is no There's no difference in the two populations. There's also a lack of overall symmetry in many floor fracture craters. Models of viscous relaxation produce a radially symmetric relaxation of the crater as you move outwards. However, many of the craters have uplifts that are offset from the center, close but not exact, and also not symmetric about the crater itself. There are also moat features in many of the craters, which thus far have been unable to be reproduced in models of viscous relaxation. Also, the location of many craters away from the basin edges is unsupportive of formation by viscous relaxation because we require very high thermal gradients out in the middle of the highlands. Additionally, there is a significant population of small floor fracture craters, and when I say small, I mean diameter 30 kilometers or smaller. And viscous relaxation is a size-dependent scaling property, and so if it were to be affecting these small craters, you'd almost certainly see relaxation in the topography around them, which you do not observe. It is only the crater itself that has this shallowing effect. So based on all of these morphometric data, we believe that magmatic intrusion is the most possible formation mechanism for floor fractured craters. So we then further examined the actual mechanics of a magmatic intrusion and whether or not it is a viable process. So we're going to run quickly through the steps and then we'll examine each one in detail. First, a dike propagates from the mantle driven by a certain driving pressure. The dike then stalls at a low density zone caused by the brecciated lens beneath the crater. And just a note, I call it a density barrier. I don't mean that there is an actual physical barrier there, but it is this low density transition between the normal highland crust and the brecciated lens. The dike then halts vertical propagation and begins to propagate laterally, forming a sill beneath the brecciated lens. The sill inflates, forming a laccolith, which bows the overlying crater floor, creates fractures in it because of the stresses. And most significantly, if the yield stress is exceeded at the edges of the intrusion, then the laccolith will have faulting at the edges and a gross uplift of the entire floor will occur. So first step, a dike propagates from the mantle with a given driving pressure that is equal to the total magma pressure minus the lithospheric pressure. And this driving pressure has to be enough to exceed the fracture toughness of the rock it is intruding into, and then raise the negatively buoyant magma through the crust. Step two is when the dike encounters this low density zone caused by the brecciated material beneath the crater. Here I have density data from a study by Hoing and Jozwiak with the density of the magma, the density of the breccia material, and the density of the lunar crust. As you can see, the density of the breccia is significantly less dense than the density of the crust, and this will have significant effects seen later. This equation is taken from Rubin and Pollard and modified slightly for visual clarity. The two important terms here are the driving pressure of the magma, and then also this delta rho term, which is the difference in density of the magma from the material it is intruding into. And for a given, there's a positive correlation between the driving pressure and the density difference, such that the greater the density difference, the more pressure is required to propagate the negatively buoyant magma through that material. So on this slide, there are numerous calculations for the amount of driving pressure that is required for a magma to reach the lunar surface, propagating through either normal highland material or through breccia lens material after some point beneath the crater. And the most important thing to note here is that a dike will require an additional 8 megapascals of driving pressure once it reaches the base of the breccia lens to continue propagating. This is a large amount of pressure for the dike to be required to build up, and so it stalls. Therefore, this idea of a breccia lens density barrier is a viable option for halting vertical propagation of the dike beneath the crater. However, that's not the end of the story for the dike, because there's still a large amount of driving pressure there, which will exceed the lithostatic pressure from the sides and cause fracturing and lateral propagation. So the dike will then continue to propagate laterally and become a sill, and it will propagate along the very barrier of the breccia lens due to a difference in stress intensity factor in the breccia and the crust material below that. So the dike propagates to the edge of the breccia lens, and once it reaches the edge of the breccia lens, it encounters a uniform stress state, which will then halt the propagation of the dike. The magma then continues to fill the sill. Crystallization of the magma at the periphery causes the magma to concentrate in the center and causes extreme flexure, shown here, in the overlying crater floor, which would result in a flexurally domed profile for the overlying crater. Another possibility for the sill filling is a rapid filling of the sill, which distributes magma throughout the entire volume of the sill. This causes greatly increased yield stresses at the periphery, which could exceed the yield stress of the overlying breccia, causing faulting, and this overall piston-like uplift of the central crater floor. Therefore, we see both flexural doming and piston-like uplift are clear consequences of sill intrusion. And excitingly enough, these are actually observed in the topography data for several floor fracture crater types. As the crater Gassendi has an overall flat floor profile, which would be consistent with piston-like uplift. And the crater Gaudibert, with its domed central interior, would be consistent with this flexural doming model. So further work needs to be done to distinguish the actual shape of the intrusion. So are the tails of the intrusion thin and tapered, or are they blunt and snub-nosed? Are both present? And is it necessary to go through both stages of this, or can a crater only experience one of them? So further work being done is very exciting with the GRAIL mission in flight now. So we are plotting the intrusions and the crater dimensions to estimate intrusion mass and the associated gravity anomaly. And these can provide predictions to be tested by the GRAIL mission. GRAIL can also help determine the intrusion shape. So if you see gravity anomalies concentrated in the very center of the crater, it would be more favorable of a thin tapered intrusion that only flexes the central region. Or if the gravity anomaly covers the entire crater floor, it would be more favorable for a large intrusion that has a piston-like uplift of the floor. There's also the question of crater size dependence and intrusion morphology. Are only small craters flexurally uplifted and you need a large crater to have piston-like uplift? Or is there a mixing, and there a mixing in the gravity signature? These are all things to be investigated. So, thank you.
Good time for questions before lunch. Yes.
Thank you. That's very nice, Lauren. Appreciate that presentation. I just had a question about the initial stage of your model regarding the dike propagation. Are you thinking that it's more likely for these dikes to propagate underneath the craters because of perhaps fracturing that occurred during the cratering process, or is it possible that these dikes exist laterally elsewhere but just don't have any way to have a surface expression?
So I actually think both are possible to some extent. That's also more work I'm hoping to explore with GRAIL, is to look for intrusion signatures not associated with the crater. But I also do believe that these dikes are able to reach so far into the lunar crust because of possible fracturing or decreased stress state caused by the actual cratering event.
Hi. When you started talking about flatter floors, it got me immediately thinking about Mercury, which is everywhere you look, you see flat floor craters. Do you want to compare, or could you compare some of the things that you've been looking at to craters we see on Mercury, and are there similarities and differences? Or?
So currently there is one observed possible floor fracture crater on Mercury, and we've looked at a lot of craters on Mercury, and it is actually very similar to Gouda Bear. It's got two sort of central domed lobes. So it doesn't seem to me that this process is operating in the same way if it's operating on Mercury, and this could be a result of the amount of pressure needed to fracture the Mercury crust to raise the magma. It's just a thought that in Mercury you typically see very large effusive volcanic events as opposed to some of the smaller ones you see on the moon, and I think this is further support of that, that you won't see small intrusive events.
Okay, if there's no further questions, you're all free to go to lunch, and the focus group